let's start this. Good. I guess I better turn the lights on. Such a weird. Okay, so today we're just going to start chapter 6. Chapter 6 is on annuities, so that's a new concept, but we've actually seen all of the things before. It's just in a new light. So today we're doing chapter 6. Up the size here. Before we get into annuities, we're going to start with just talking about effective and equivalent interest rates. And so we use effective rates to build up to equivalent interest rates. But the idea is that we want to be able to switch from compounding quarterly, for example, to compounding annually, right? And so, so we need some way to be able to switch our periodic interest rate to be compounding at a different rate. Okay? And so 6.1 is going to be on effective and equivalent interest rates. So the effective rate, we'll just define it first. The effective rate, which we denote by, so it's an interest rate, it's a periodic interest rate I, but then we do a subscript little EFF, is the annually compounded rate that produces the same future value as the given nominal rate, right? So if I give you 5% compounded biweekly, right, we can convert that to an effective rate, and it would be the equivalent rate, but for an annual compounding. Okay. And so it is the annually compounded rate that produces the same future value as the given nominal rate. Dun, 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 dun. If you've got your formula sheet, right, now we're flipping to the back, and same as last time, right? Same as for simple interest, compound interest. We're just going to work our way through these formulas. When do we use them? When do we apply them? And we'll just work through examples, right? So we're going to talk about just interest rates for now, which is actually the first 1, 2, 3, 4, 5, the top 5 formulas. Those are the ones that we're going to talk about now. And so if you've got the formula sheet, right, we know that the effective interest rate, or the effective periodic interest rate, is 1 plus I to the power of F, then minus 1. So this is on your formula sheet. Where I is the periodic interest rate that's the same as before, right? Same as before. So nothing changes meaning really, just application. And F is the compounding frequency. So we'll do an example, and I think I don't have them here. Let me just go grab them. Move them to here. Oh. It's all weird. So example 193 says, what is the effective interest rate of an investment which earns 4.8% compounded quarterly? And so essentially the effective interest rate, remember, is asking, okay, if we're compounding quarterly, right, 4.8% quarterly, what would the same rate be but compounded annually, right? We needed to arrive at the same future value. And so we know that R is 0.048 and F is quarterly, so 4, which means that I is R over F, that's still true, which is 0.048 over 4. 0.048 divided by 4 is 0.012. So that's the periodic interest rate that we want to find the effective rate of. And so we use the formula. The effective interest rate is 1 plus I to the power of F, then minus 1. That's going to be 1 plus 0.012 to the power of 4 minus 1. So plus 1 to the power of 4 minus 1. I get an answer of 0.048870933. Therefore, a rate of 4.89, if I'm just percent, if I'm rounding the percentage to 2 decimal places. So a rate of 4.89 compounded annually, because the effective rate is always compounded annually by definition, compounded annually is equivalent to 4.8%, right? That was from the question, compounded quarterly. Let's just go back and just highlight, because I guess I didn't mention it, but we knew we had to find the effective rate only because it said, what is the effective interest rate, right? And so this is I subscript EFF. Any questions about that one? Nice. We've seen the day before the test, right? We saw that we could have continuously compounded interest rates, right? So that's when they're continuously compounding, right? You can't even break it up into little moments. It's even faster than seconds, right? And so continuously compounded are these special case scenarios. And really, whenever you see an interest rate with an E or an LN in it, right, as long as we're talking interest rates, it's going to be for continuously compounded stuff, right? So from last day, for compound interest, right, we had the future values, the present value times e to the power of RT. So we have that e for continuously compounded things, or interest rate. So we'll talk about it. It's not going to be a huge deal. Might be just a quick kind of short answer type of situation. So don't get bogged down in it. But if we have a continuously compounded rate, the effective rate is e to the power of r minus 1. Right? That's only for continuously compounded, because the problem with continuous compounding, if we tried to use that formula that we used earlier, right, is there is no f. F would be infinity, which doesn't really work, right? And so, so that's why we need this special formula. Is it going to be a major player? No, absolutely not. Right? But we need to know how to deal with continuously compounded. And that was part of our example when we introduced continuous compounding was, okay, well, I've got this continuously compounded rate. If I had to achieve the same future value with an annually compounded rate, what would that rate be? So we did that in class, right? And we found that the difference between the rates isn't actually that big, right? So it's pretty minimal. And so the effective rate is what we were finding before. But we just said, what annually compounded rate would we need, right? And so technically we were finding the effective rate. So where R is the nominal rate. But that's the only thing that we need to fill in here, right? E to the power of R minus 1. Let's do example 197. An investment earns 6% continuously compounded interest, right? And so, right, 6% continuously compounded. So if we're continuously compounding, we need these special formulas. What is the effective rate of interest, right? And so we know that R is 0.06. And I guess we could say, just to highlight, that F is continuous. And we want to find the effective interest rate. Well, the effective rate is e to the power of R minus 1 for continuously compounded interest rates. So we have e to the 0.06 and then minus 1. On your calculator, right, I'll just remind you here, you have to have 0.06 on the screen, and then hit the second button and then the ln button, which is the e to the x function. And then hit equals, just in case, 1.0618365547. So just make sure that you get that same value. And then we have to subtract 1, right? Because if we have an effective periodic interest rate of 106%, that's really good if we're getting it, not so good if we're paying it, right? But it doesn't really make sense. And so 1.0618365547 minus 1 0.061836547. One checking point that you always want to have is for I should be small, right? The effective interest rate is compounded annually, right? So it should be a percentage that we're used to seeing, right? 6%, 4%, 5%, things like that, right? Here, because our original rate was 6%, we should expect our effective rate to be around 6%, right? They're not going to make huge, big jumps, right? And so just have that as kind of a checking point. Any questions about those? No? Cool beans. All right, so here's the meat and potatoes of it all. Equivalent interest rates. Okay, so here's a spoiler alert. In annuities, first I'll tell you what annuities are. I know, mega spoiler alert. Can't hold it anymore. Annuities are when we're making regular payments, right? And so in compound interest, right, I'm calling it compound interest, we'll still have interest compounding, but we had, you make a payment at 1 year, you make a payment at 5 years, what are they worth at 4 years, for example, right? We were doing things like that. Annuities are going to be things like car payments, mortgage payments, right, where you've got these monthly or bi-weekly payments, and these are at regular scheduled intervals. Technically, you could take all these, 120 payments, let's say, calculate the future value, future value, if you wanted that, present value for all these payments, but that feels like a huge pain in the butt, and it would be, right? And so we've got different formulas to handle that, right? You definitely could apply the things that you've already learned, but you don't want to do that, right? So we've got these different formulas that we're going to introduce, but we've seen these things. It's just the idea of these regular payments. Now, the problem is, what we're building up towards is, let's say that I'm making monthly payments, but my interest is compounded semi-annually, for example, right? As a rule, I need to have the same compounding frequency as the payment frequency. And so I need to be able to adjust my compounding frequency, right, or the periodic interest rate to match the payment frequency. So that's why we need equivalent interest rates. Equivalent interest rates. And I'd say this is, yeah, question? Yes. I shouldn't have. I should have finished it off, but it's okay. Yeah, you should do 6.18% is equivalent to, but I got lazy. Yeah. Thank you. Keeping me honest up here. That's done, over and done with. All right, and so equivalent interest rates from this whole section, this next part is the one that you need to pay attention to, or the only formula that you'll really, really need from this section. So equivalent interest rates are two interest rates that have the same effective rate. That have the same effective rate. So we use the effective rate as kind of a middleman, right? Because what we're doing technically is we're taking some rate compounded quarterly, let's say, finding its effective rate, and then undoing the effective rate to be compounded semi-annually, for example, right? And so we're kind of using the effective rate as kind of a stepping stone. I'll show you how it came about, how this formula came about, but you don't need to know that. It's just to show you what's going on. And so if we've got an effective interest rate 1, and we're going to force it to be equal to the effective interest rate 2, right? Because we're forcing these equivalent interest rates, right, to have the same effective rate. So then we can replace the effective rate with 1 plus I, and then I'll put a subscript 1 to the power of F1 minus 1 is 1 plus I2 to the power of F2 minus 1. Just using the formula for an effective rate. Forgetting about continuously compounded stuff. That's not relevant for us right now. And I can move the minus 1 over. Let's just do that. We'll just be careful. 1 plus I1 to the power of F1 minus 1 plus 1 is 1 plus I2 to the power of F2. Those are going to cancel, right? Gone, gone. Minus 1 plus 1 makes 0. So now I've got this F2 in the power and F1 in the power. I'm going to solve for I2. Right, we have to pick one of these to solve for. I'm going to solve for I2, mostly because that's what's going to match your formula sheet. Right? So I2 is the new interest rate, or the new periodic interest rate at the new compounding frequency F2. Right? So if I'm solving for I2, I need to take the F2th root of both sides. How do I take the root of one side? I do 1 over, or to the power of 1 over F2. Right? And so what I have is I have 1 plus I1 to the power of F1 times 1 over F2 is 1 plus I2 to the power of F2 times 1 over F2. So this becomes 1 plus I1 to the power of F1 over F2, which is 1 plus I2. Because F2 over F2 is 1, so now I've got a power of 1. Solving for I2 and doing my switcheroo in the same move, right? I2 then must be 1 plus I1 to the power of F1 over F2 minus 1. And this is on your formula sheet. I'm going to put a double frame around it. That's how important it is. Anytime that we've got annuities, we've got another step, right? So moving from, if we kind of look at how we've progressed, right? We went from simple interest, where we didn't have any compoundings, right? So we didn't care about that. Then we moved to compound interest, where we had to first calculate the number of compoundings and the periodic interest rate. Now we're moving into annuities. Not much has changed, except in the beginning, we have to start by not just finding the periodic interest rate, but also maybe the revised periodic interest rate, or I2, right? If we have to adjust our compoundings to match our payment frequencies. So this one's going to be important. We use I2 equals 1 plus I1 to the power of F1 over F2 minus 1 when we need to change change the compounding frequency from F1 to F2 and I'll just put in brackets to match the payment frequency in annuities, to match the payment frequency in annuities. So I2 will be the periodic interest rate, at the new compounding frequency. It's messy. So just to recap here, I2 is 1 plus I1 to the power of F1 over F2, then minus 1. I just want to do a list of the variables so that we have them. So where I'll start with I1. I1 is the original periodic interest rate. Thinking in terms of what we've been doing, right? Our I so far has been I1, right? That would be our starting point. And F1 is the original compounding frequency. If you're thinking about when we were using the calculator, right, probably didn't get too comfortable with the calculator quite yet, right? But remember that we had the C per Y, right, the compoundings per year, but then there was also P per Y, right? That P per Y would be our F2. And so I'll just put in brackets here on our calculator, right? F1 is the compoundings per year. If we're talking about I2, that's going to be the new periodic interest rate. And so F2 is the new compounding frequency. Right? And then I'll put in brackets. Since this needs to match our payment frequency, since this will need to match the payment frequency, right, on our calculator, F2 is going to be the payments per year. And those are the only variables that are in this formula, right? I1, F1, I2, F2. Right? And it's just a way for us to go from one compounding to another. Right? Just switching from one periodic interest rate to another. Okay, let's do an example. Example 198. Let's do. So an investment earns 5% interest per year, compounded semi-annually. How much interest should alternative investments, which are compounded quarterly, pay? Right, and so now we're moving from compounding semi-annually to compounding quarterly. Right? And so in terms of R's, I's, F's, all that fun stuff, right, we've got R1, let's call it, is 0.05. F1, that's the initial frequency, is semi-annually, right? So that's 2. And so I1 is 0.05, or I should use the formula. It's still R over F. It's just R1 over F1, which is 0.05 over 2, 0.025. So now, find I2, right, if F2 is quarterly, 4. And then we could take it back to the nominal rate, but I'm just going to find the periodic interest rates and leave it at that. So find I2 if F2 is 4. So I2 is 1 plus I1 to the power of F1 over F2, then minus 1. 1 plus 0.025 to the power of F1 is 2, and F2 is 4. And I read those powers as moving from compounding semi-annually to compounding quarterly, right? They kind of appear in that order. Minus 1. So we've got 0.025. So 1.025 to the power of 2 divided by 4. And then minus 1, I get 0.012422837. In your calculations, you have to use that whole number, right? So this would be one of those situations where you definitely want to store that number and just use the recall button, right? And so like I said, I'm not going to find the nominal rate, right? I'm just going to keep it as the periodic interest rate. But I will say that therefore a periodic interest rate of 1.25%, or sorry, 1.24% compounded quarterly is equivalent to a periodic interest rate of 2.5%, right? That was our initial periodic interest rate, compounded semi-annually.
you meant to say 5%, 2.5.
But I'm saying the periodic interest rate, because I didn't convert this 1.24% to a nominal rate. I cheated, and I'm just saying the periodic interest rate. Right. And the periodic interest rate of the original was 2.5%. Or we could have said 1.24 times 4 and then compared it to 5.
So F1 is not the original then?
F1 is the original compounding frequency, and F2 is the new compounding frequency. Cool. Just like before, right, I don't want you to kind of get stuck on these continuously compounded things, but we can find I2 even if we're moving from a continuously compounded rate. And so these are kind of special case. But so for continuously compounded interest, we can convert to a different compounding frequency by I2 is E. So there's that E again telling you that, hey, this is going to be continuously compounded to the power of R over F2 minus 1. This is also on your formula sheet. If you think about it, did we need the effective rate calculation at all? No, it's just a special case, right, where F2 is 1, right? Because then the effective rate is just when we're converting it to annually, right? So whatever compounding we've got, just converting it to annually. But you could just as well just use these formulas with F2 equals 1, right? And find the effective rate, right? Just by knowing the definition of the effective rate. So you don't really need the effective rates anymore now that you've got these new and improved formulas. Right? As long as you keep in mind that the effective rate is when F2 is 1, right? Annually compounded. So where F2 is the desired compounding frequency of I2. Or, right, we could go the other way. And again, these are very kind of special case, not that important to know, right? But we have to talk about them. If we want to move to a continuously compounded rate, right, we need some way to do that as well. And so we have a formula for that. Or we can convert a given rate to a continuously compounded rate continuously compounded rate by the formula R is F1, right, the initial frequency that we're moving from, times the natural log. Remember, the natural log is the inverse of the e to the x, right? And so it's also in the family of continuous functions, but now we're kind of undoing it. And so times the log of 1 plus I1. This is the one on the formula sheet. But I think just to be extra confusing a little bit, the textbook, I think, just uses R is F times the log of 1 plus I. But I think you've got the nicer one on the formula sheet where it actually specifies that, hey, F is from the frequency that we're moving from, and I is the original periodic interest rate. And so this is in the textbook. But they're the same. Let's do example 202. Oops. An investment earns 5% interest per year compounded quarterly. What is the equivalent continuously compounded rate? Right, so if we're moving from quarterly to a continuous compounding, if we've got 5%, then we're going to use, okay, so we've got, what the? We've got R1 is 0.05. F1 is 4. And so I1 is R1 over F1, which is 0.05 over 4, which is 0.0125. Okay, so now we've got I1, we know F1, and so now we've got all the components that we need to figure out what R is, and R is going to be continuously compounding. So we've got R is F1 times the natural log of 1 plus I1. So R is going to be F1, which is 4, times the natural log of 1 plus 0.0125. Which I'll simplify here, 4 times the log of 1.0125. And again, just as a reminder, to do the log of 1.0125 on your calculator, you have to have 1.0125 on the screen and then hit the LN button. And then hit equals, just in case, you don't need to, but just in case, is 0.01242252. So just double check that that's what you're getting. So we need 4 times 0.01242252. So times that by 4 then, And we get 0.04969008. So what does that mean? Well, we moved from a rate of 5% compounded quarterly is equivalent to 4.97% compounded continuously. Not a huge difference. Well, I mean, sort of, but not really. So therefore, 5% compounded continuously, or sorry, compounded quarterly, mix those up, quarterly is equivalent to 4.97%. That's compounded continuously. We'll do, I don't think we did an example for that one. So let's do example 203. And then we'll have seen all the different scenarios. What monthly compounded rate is equivalent to 9.5% compounded continuously? And so we need to find, so we've got 9.5, we've got an R of 9.5%, or I'll just write 0.095. And F is continuous. Find I2 with F2 equals monthly, so 12. So we're moving from a continuously compounded to a monthly compounded rate. And so that's when we use the I2 equals e to the R over F2 minus 1. And we're solving for I2, so we need e to the power of R, which is 0.095, divided by F2, which is 12, and then minus 1. You're going to do 0.095 divided by 12 first, e to the power of 0.0079166667, let's call it, and then minus 1. We already did the exponent, so you have that number on your screen, and then second ln takes you to e to the x, and then equals, so I get 1.007948086 minus 1. Don't forget that minus 1, right? Otherwise, you're talking 100% every month. That doesn't happen. And so you get 0.007948086. Just to be proper, I should have been solving for R2 technically this whole time, but I didn't. So solve for R2. Well, we've got I2 is 0.0079480886. And we've got F2 is 12. And we know I2 is R2 over F2. And so R2 must be I2 times F2. So R2 must be 0.0079480886 times 12. So you've got that on your screen, right? As long as you remember to subtract the 1 times 12. So R2 is 0.095377036. And just to have room on this page before I get that page break, I'm just going to scoot this up a line. I was writing solutions on a paper copy the other day, and I didn't leave myself enough room, so I just wanted to like drag and drop it. Doesn't work that way. It's a big pain in my butt. Here, it's so easy. Just erase stuff, mass delete. So therefore, a rate of 9.5, and I'll round it to 4%, compounded monthly is equivalent to a rate of 9.5% compounded continuously. Nice. Any questions about that? So just kind of working with moving from different compounding frequencies, right? But like I said, the main player out of all these top 5 formulas, right, is going to be the I2 is 1 plus I1 to the power of F1 over F2 minus 1, right? If that's the only one that you focus on, that's fine. But once you've kind of got the hang of that one and you stumble upon you need a continuously compounded rate, or you have a continuously compounded rate and you want to move away from that, then you know that you've got options, right, over here on the right-hand side on your formula sheet. All right, I think we're ready for annuities. I already said what they were, but still. 6.2 annuities. So an annuity is a series of equal payments, and you did that a lot, right? You had to solve for X. What are the equal payments if we want to have a total of $10,000 at the end of 4 years and things like that, right? And so equal payments, so a series of equal payments at regular intervals And like I said, the methods that we've covered already, yes, you could use those, but they would be very, very tedious. So first we have to define some things like a payment interval. Nothing crazy here though, right? It's the amount of time between payments. The amount of time between payments. We're also going to have a periodic payment. That's the amount of the equal payments in the annuity, right? So if you, let's say, finance a car, right? And we've all seen on the side of the highway, you can have this car for $94 biweekly, right? Those are equal payments. You know you're paying equal payments, but you're paying different amounts of interest, right? Just because of how money works, but it's been calculated so that you can pay an equal payment amount, right? And so the periodic payment is that kind of monthly payment or biweekly payment amount. So it's the amount of the equal payments in the annuity. It's denoted by PMT. Right? Both in our calculations, if you just kind of have a glance at these formulas, right? They look huge, but we're going to work through them and just kind of dissect them like we did with the other ones, right? So don't worry. But there's a PMT in there, right? That's going to be the payment amount. And also on your formula, or on your calculator, right? You've got a PMT. So that's going to be that payment amount. We've been using 0, right? Because we haven't had regular payments, but now we've got these regular payments that we have to deal with. And then just to say that the term is just the duration of the payments. Here's a big change. Not really once we kind of get down to the nitty-gritty, right? But first glance, the biggest change that we'll have is that, so we've been using lowercase n to be the number of compoundings, right? Now for annuities, n is going to denote the number of payments. Okay? If you think about it though, that's because we're going to change our compounding frequency to match our payment frequency, and so they'll be the same. Right? So I'll just highlight it here. In annuities, N is used to denote the number of payments. But just as an additional note, the number of payments will be the same as the number of compoundings after we have adjusted our compounding frequency. After we have adjusted our compounding frequency to match the payment frequency, using I2 is 1 plus I1 to the power of F1 over F2 minus 1. So it is the number of compounding still, but it's just going to be easier if we think about it in terms of the number of payments. All right. So we already know that there's going to be that extra step of adjusting our compounding frequency if it doesn't match the payment frequency. And so what we're going to have for annuities is we're going to have some different scenarios, right? And so we've got a special name for annuities where the payment frequency matches the compounding frequency. And we just call that a simple annuity. And so if we talk about annuities, what I'm going to do is I'm going to make a column of options on the left-hand side and then a column of options on the right-hand side, because they can be kind of mixed and matched. Okay? So we'll start with we can have a simple annuity. A simple annuity, which is, and I'll just use a different color here, is when the payment frequency matches the compounding frequency. That's not a situation that we're going to spend a lot of time on, right? The one that we will spend time on is a general annuity. So a general annuity is when the payment and compounding periods are different. Payment and compounding, I'll say frequencies. Frequencies are different. Clean that up. Okay. So here, the simple and general annuities is just talking about how does, and if I use this shorthand, the compoundings per year, if I use the calculator shorthand, right, this is kind of the title of this column, the compoundings per year, does it match the payments per year, right? If it does, oh, should be a Y. You've got a simple annuity, right? If you don't, you've got a general annuity, and you'll need to calculate I2. need to calculate I2. The next column doesn't have to do with the compounding frequency or the payment frequency. It has to do when the first payment and when these payments are being made. Because things can be made, or payments can be made at the end of each month, bi-weekly period, weekly period, right? So they can be made at the end of a payment period, or they can be made at the beginning of the payment period, right? And so the other question we ask is, when are payments made? Our first option is an ordinary annuity. Which is when payments are made at the end of each payment period. So payments are made at the end of the payment period. Or you can have an annuity due. An annuity due is when the payments are made at the beginning of each payment period. Payments are made at the beginning, beginning of the payment period. Clean up that beginning, actually. It's kind of a key word. In chapter 6, we're going to talk about ordinary annuities. The only thing that's changing in chapter 7 is we're going to be talking about annuities due. So instead of payments at the end, we've got payments at the beginning. It changes our formula, but if you have a look at your formula sheet, right, you've got, I always mix up the names, ordinary annuities on the left-hand side and annuities due on the right-hand side. And if you have a look and really kind of look at them, the only thing that's changing on the right-hand side is that you've got a 1 + I tacked on. And that's because there's a little bit of interest that you get or pay depending on what's going on, right? If you pay at the beginning, right? Because you've paid it off a little bit sooner, and so then you're kind of chipping away a month faster, let's say, than you would if you were paying at the end of each month, right? And so we have to make that tiny adjustment, but that's the only thing that changes for annuities due, right? And so that's why we don't spend a lot of time in chapter 7, because it's like, hey, here's everything that we just did with a slight tweak, right? Nothing major. Here's the thing though. So an ordinary annuity can be either simple or general, and an annuity due can be either simple or general, right? And so we can have this kind of mix and match situation, right? Because one has to do with the compounding frequency and the payment frequency, and the other has to do with when are the payments being made. So, and like I said, as long as you've kind of figured out when your payments are being made, and in chapter 6 that we're doing right now, right, we're going to talk about ordinary annuities, right? So these payments will always be at the end, right? That's going to be the default. If payments are being made at the beginning, it has to say explicitly, right, at the beginning of each month, at the beginning of each year, that kind of thing. Okay. What I would like for you to do is just treat all these annuities as if they're general annuities, right? Because, well, let's have a look at what the formula does. The safest way to work with annuities will be to treat all annuities as if they're general annuities. Will be to treat all annuities as if they are general annuities. That is to say, start all annuity calculations by finding I2, right? Regardless of if you see that you need to or not, right? It's just always safest just to have that as your starting point. Okay, first I have to find I1, and then I'm going to find I2, and then I can figure out my calculations, right? And so that is to say, always start by finding I2, right? If F1 equals F2, right? That's the same as a simple annuity, right? The payment frequency is the same as the compounding frequency. And so if I'm paying monthly and I'm compounding monthly, right, then that's F1 equals F2. Then we can say that I2 is 1 plus I1 to the power of F1 over F2. But if F1 equals F2, if F1 equals F2, then F1 over F2 is 1. And then minus 1. So what we have is I2 is going to be 1 plus I1 to the power of 1 minus 1. So I2 is, oh, no bracket, 1 plus I1 minus 1. So then I2 is just I1. That's what I mean. It's a pretty good safety net, because even if you did go through and do all those calculations, yeah, it's a little bit of work, but when you're doing it on your own, it's not that big of a deal, right? And so, but typically what you'll find is as soon as you see that F1 equals F2, you're going to say, oh, there's no point in doing this, right? But it's always good to have that first check-in point and say, oh, I'm going to calculate I2, and then find out, oh, I don't need to, right? You've got a simple annuity. So as a rule, I would say always start by finding I2, and then you can quit if you find that you don't need to, right? Because they're the same, and so nothing's going to change. Or if you just go through and find that they're the same, then that's fine, because they will be if they have the same frequencies. And so on our calculator, or actually what I want to do before I talk about the calculator, so we're going to have our compounding frequency is F1. Which is our compoundings per year on our calculator. There, I said it, calculator. And our payment frequency which is going to be our F2. This is always going to be true, which is going to be the payments per year on our calculator. What's nice about the calculator is you actually don't have to do any, you don't have to find the periodic interest rate as we found earlier, right? We have to just give it the interest per year, the nominal rate, and the compoundings per year. And now we're able to give it the payments per year, and it'll just calculate I2 for us, right? And so the calculator, if you didn't like it before, you will like it after this section, right? Because it saves us a lot of time. But we're still gonna do it by hand. All right, and so what I want to do is, I'll just say ordinary. See, I always mix these up. Yeah, ordinary annuities, that's what we're doing. Ordinary annuities. We've got a future value formula. So just like before, right, I introduce the formula and then we'll kind of talk about all the components. We'll do some examples solving for the future value, the present value, and then solve for N, solve for T, right, all those fun things. So we're going to do the same thing. And so for ordinary annuities, right, we've got the future value is the PMT, and then we've got big square brackets and 1 plus I to the power of N minus I, or sorry, minus 1 over I. Where, of course, the future value is the future value. PMT is the periodic payment amount. I is the periodic interest rate. Which you're going to use I2. Or in the special case where the payment frequency and the compounding frequency are the same, you can use I1 because it'll be the same as I2, as we just showed, right? And so I is actually I2, and N is the number of payments. And then it's minus 1 over I again. Notice that there's no present value here. right? And so the idea is that you're only going to be able to move one way, right? And so you're either paying off a car, right? So then you've got some present value and you're making payments and chipping away at the loan that you got. The future value of that would be zero, right? If you paid off the car, the future value is zero, right? If you're saving towards some amount, you're starting with nothing, right? So then the present value would be zero. And so we've got two different formulas, and that's why the formula sheet looks so scary, is because you've got the future value formula and then you've got the present value formula, right? And so depending on what the question is, you're gonna have to pick which formula to use, right? They have a very similar layout, but I should highlight this because this one's on your formula sheet, of course. The present value is the PMT, and then square brackets, and then 1 minus 1 plus I to the power of negative n over I. And this is also on your formula sheet. We have the same variables, right? So where PV is the present value, and all other variables, I'll cheat, all other variables are the same as above. So I'll make a note here that depending on if we want to find the future value or the present value, right, we'll need to pick the appropriate formula. So depending on if we need to find the FV or PV, we will need to pick the appropriate formula. All right. So I want to talk about timelines for annuities, right? Timelines for annuities are going to have a similar layout, but if I'm making monthly payments for 4 years, for example, right, thinking about a car payment maybe, right, then I don't want to have to make little ticks and put the dollar amounts for 12 times 4 ticks. That's terrible, right? So I don't want to do that. And so for these annuities timelines, so timelines for annuities, right? What I want to see is the first 3 ticks and the last 2 ticks at minimum. And that's, I'll go for minimum when I do mine, right? So that's fine. But I don't want to see any less than that. At minimum, you must show the first 3 ticks and the last 2 ticks. Meaning it'll look like this. Right, if you start today, and then I make a payment at 1 month, 2 months, and then here, let's use the 4-year mark. 4 times 12 is what, 48? 48 months, or 4 years. I've shown the first 3 ticks, and I want to see the last 2 ticks, so 48 months, moving by months. The second to last tick is 47 months. And then what I do is I separate these with a ... Right, just to indicate that things just keep going this way until you hit 48. And then what I'm going to do is I'm going to put the payment amount under each of these ticks, right? And so I don't start today because the payments are being made at the end of each month, not until chapter 7 that they might be done at the beginning, right? And so I've got a payment of whatever amount, so a PMT, right? That's the payment amount at 1 month. And I've got a PMT at 2 months, I've got a PMT at 47 months, and a PMT, the final PMT, at 48 months. Instead of drawing arrows for all of these, let's say we're calculating a future value, what I'm gonna do is I'm just gonna funnel all these, right, kind of curly bracket them together, they all come together, and I can do 1 arrow for the future value. Otherwise, it's hard to show these things, right? And so all the payments can be, and I'll put in quotes here, funneled, right? Just putting into a funnel here, funneled into a future value or present value. In this case, a future value, but. And then same thing, right? I'm going to put N is 48, right? I already had to find that N, right? But I'm just going to put it on the arrow. That's the number of payments. If I'm making monthly payments for 4 years, I've got 48 payments. All right. Let's do example 204. Oops. Martha contributes $10,000 each year to her RRSP. At a rate of interest of 7% per year, how much will she have after 25 years? And so she contributes $10,000 each year. Right, so let's highlight some things that we know, right? We're told that the payment amount is $10,000. So just in the order that it appears. And these payments are made each year. So if I just use the shorthand, payments per year is 1. Okay. The rate of interest, R, I'm going to use R subscript of 1 is 0.07 per year, right? So 7% per year is a sloppy way of saying compounded annually, right? 7% annually. And so F1 is 1. Or you know what? I'll use the same convention here. Compoundings per year is 1, which is also F1, which in case you weren't sure, right, that's a good kind of trigger to say, well, then the compoundings per year must be F2, right? Or you can just memorize that the compounding or the payment frequency is F2. Okay. So how much will she have after 25 years? So first thing I'm going to do is calculate the periodic interest rate. I see that F1 equals F2, but just as a quick check, right, I'm going to calculate I1 is R1 over F1, which is 0.07 over 1, which is 0.07. Well, if I calculate I2 as just a checking point, it's 1 plus I1 to the power of F1 over F2 minus 1. I2 must be 1 plus 0.07 to the power of 1 over 1 minus 1, which is 1 plus 0.07 minus 1. So I2 is also 0.07. Right, so no harm in doing that. It's just a tiny bit of extra work, but at least you know you're playing it safe, right? If you just start by calculating I2, so then this is the I that you're going to use in your calculations. Okay. All right, let's do our timeline. And I've got a page break to deal with here, so I'm going to put it down here. So she's making payments, let's assume starting today, and she's going to go for 25 years. Oh. I put 25 years up a little bit higher, only to make room for the payment frequency, which might not be this. In this case, it is yearly, so it is just 25 years. So I guess I could move it down. I'll just use Y, 25Y. So I'm making payments every year. So I start today, and then here's at 1 year, 2 years, and then ... 25 years, and the year before that was 24 years. The payment amount goes below the tick, right? And so each payment amount is 10,000, 10,000, 10,000, and finally 10,000. The question asked, how much will she have after 25 years? And so we need to find, okay, well, what's all this as a future value, right? Collecting all these payments. And yeah, absolutely. Like I said, you could have drawn out all 25 ticks, put 10,000 below each of them, and drawn 25 arrows and calculated 25 future values. But you'll end up at the same answer as with the formula that I gave you. So why? Why would you do that? Right? You can, but no, we don't do that. And so we want a future value out of these guys. And so I'm going to funnel these and say, I want a future value here. N is the number of payments. So N is 25. And I already calculated I2 is 0.07. And so the future value formula, right, we have is the PMT amount times 1 plus I to the power of N minus 1 over I. So we've got a payment amount of 10,000 times 1 plus 0.07, right? I2 was 0.07, so that's what we use. To the power of n, which is 25, and then minus 1, and then minus or over I, which is 0.07. Careful when you're doing these calculations, right? You're going to start with the 1 plus 0.07 to the power of 25, then minus 1, then divide by 0.07. And it's typically just something that you're going to do on your calculator. I'm not even showing all my steps, right? I'm just going to do this calculation because with all these values, it's going to be hard to stop and write our work out. 1.07 to the power of 25 minus 1 over 0.07. For this whole value, I'll stop here, 10,000 times 63.24903772, but that's just so you can check that you got the same value. And then times 10,000, 632,490.3772. Which in money would be 632,490.38. If we think about how much she paid out of pocket, right? She made 25 payments of $10,000. So she paid $250,000, but because of interest and how things kind of work, at the end of it all, she gets $632,000, right? So it cost her, well, it cost her $10,000 every year, right, for 25 years, but at the end, she gets quite a bit more than what she paid, right, because of interest. Let's call it there. I'll save this next example. Surprise, surprise, it's a present value example. Same idea, we'll use it for review next day. Any questions? Have a great long weekend. You deserve it. All right. Bye, Ellie.